Okay, last time we talked about the binomial theorem. Today I'm going to dive into calculus and derivatives, and then we're going to use the binomial theorem in the next video to prove what the derivative of a polynomial is. So that's going to get interesting. Right now we're going to dive into what is a derivative and really kind of the basics of calculus, which is really the foundation of calculus is something called a limit. And we'll talk about that a little bit as well. But let's just start with an example and kind of think about why we might even want to consider what this whole concept is. So let me just draw two axes here. Let's call this one time. And let's call this one position. And let's say this is time in hours. And this is position in miles. And let's just think about a car graphically. If a car is about to go on a trip and you start driving, at time 0, you have gone 0 miles. Then let's say after 1 hour, you maybe have gone, I don't know, let's say you've gone 40 miles. So we're going to say that that's 40. And then let's say after 2 hours, you've now gone, let's say 100 miles. So you went quite a bit faster there. And then let's say after 3 hours, let's say you stopped for an hour and you're still at 100 miles. So your graph kind of looks like this, and then you stopped. So we can, if we're trying to figure out the velocity of the car, we can think about it between, let's say, time 1 and time 2. So that's this point and this point. And if you were to draw the line, it's a pretty straight line in there that I drew, but that's the slope of that line. Because what we're doing is we're saying, okay, we went between 40 and 100 miles. So how far did we go? We went 60 miles. We went 100 minus 40. And we did that over the span of 1 hour because we did it from hour 1 to hour 2. So divided by 2 minus 1, which is 1. So we're left with 60 divided by 1, which is 60 miles per hour. So our average speed between time 1 and time 2 was 60 miles an hour. Now, in reality, the car may have gone, 50 miles an hour at some points, 70 miles an hour at other points, but the average over that span was 60 miles an hour. If you think about when you're actually driving a car, you can see your instantaneous velocity. At one point, at one moment, you look down and you say, I'm going 75 miles an hour. Then at another moment, you may be going 70 miles an hour. Well, how do you actually calculate that? Because if I were to look at one point in time, let's say I wanted to know how fast am I going at hour 1.5 right there. Our denominator here was a positive integer. It was 1. We were actually subtracting two numbers and we got a 1, and so we were able to do the division. If we're looking at one point in time, and if that's a 0, you can't divide by 0. So that becomes a problem with calculating an instantaneous rate of change. That's where limits come into play, and that's where a derivative comes into play. We want to find out how fast am I going at one single point in time, and this can be applied to things other than velocity. That can be applied to a lot of different applications, so you can see where it would come in very handy. That's just kind of giving you a background of why we might want to do something like this. So let's consider, I'm going to erase this graph and I'm going to kind of draw a similar graph for you, and we'll really kind of mathematically work this out. So instead of using time and position, those were my examples, I'm just going to use a generic variable x. That's my independent variable that I'm going to plug into my function here, which I'm going to call f of x. In the case of the car, that was position. So I plug in some x, which was time in my other example, and I get a number, which was a position in my other example. That's what a function does. It's got an input and an output. So let's just say that my graph looked something like this. And I'm going to kind of, I'm going to use some generic variables here to represent similar to what I was doing in the other one, but just with generic variables. Let's say this is A. Let's say this is B. And then I got a point right there. And then if you kind of go up, I got a point right there. So if we go over, that's f of B. If we go over here, that's f of A. All right, so like I said, we can find the slope between those 2 points in time. I shouldn't say points in time, I should say between those 2 points as our average slope between them. But we haven't found the individual points within there. So let's think about a way to do that. What if I want to find the instantaneous rate of change at f of A? That would be a slope of a line that kind of lies right next to this. Because you see this line changing over time, the slope changes, and at that point in time, right at f of A, we're looking at a slope that looks something like that. So how am I going to find that? If you imagine the distance between B and A as h, we're going to call it h, so h equals B minus A. And if we imagine this point B getting closer and closer and closer to A, we're going to get a better and better estimate of our slope at that point in time, right? Because if B were right here or right here or right here, we're calculating a slope between 2 points that are much closer on our graph than what these two are, because these two are quite a bit apart. So if we just think about the definition of the slope, it's f of B minus f of A divided by B minus A. That, if you remember in algebra, is rise over run. That's the distance there minus the distance there. And that's what we did in the other example where we were calculating miles per hour. We can also represent this, since we defined h as B minus A, we can say this is really the same as saying, okay, that's f of A plus h minus f of A divided by h, right? B is just A plus this distance h, we get to B. Then we have f of A, then we have B minus A, which is that distance h. So we can say that the derivative, or the instantaneous rate of change at point A, is equal to the limit, and it's denoted with LIM, as h approaches 0, of f of A plus h minus f of A divided by h. That is the definition of a derivative at point A. So that's the derivative of f of A. We're saying let h get as close to 0 as possible, and we're going to do our subtraction. We're going to divide by h. Of course, normally you can't divide by 0, but we're approaching 0, and therefore we can actually define this thing. You could generically define that for really any, I used A in this example, but we could do it for any x, right? Any point along our x-axis, we could do that. So let's kind of write that out. And we write this thing as f prime x. We call that a prime sometimes. The derivative of f of x is denoted with a little slash up there. is equal to, same thing as this, but we'll replace the a with an x. So we say the limit as h approaches 0 of f of x plus h minus f of x divided by h. And there you have the definition of what a derivative is, which really, all we're really doing is calculating a slope at a single instantaneous point. And that's what this limit is doing. This limit is saying we are moving things as close to that point as possible, and we're calculating that at a single point. So let's just do an example of how you might calculate something like this. And once again, I'm going to draw a graph. This one I'm going to make a simple graph. So let's just say that our function f of x is equal to 2x. What does that look like? If I draw that out, here's my f of x, here's my x. When x is 1, you plug that in, 1 times 2 is 2. So we're going to be at 0.2 here, right? When x is 2, 2 times 2 is 4, so it's going to be at 0.4. So if I draw a point there, so our line looks something like that. This, if you can see, it's a straight line, so our slope is really the same everywhere. So what would we expect our slope to be at any point? If you do 4 minus 2 divided by 2 minus 1, you get 4 divided by, or you get 2 divided by 1, and you're left with 2. So we should have a slope of 2 everywhere, because this slope doesn't change. But let's just test that out. So let's just say I want to calculate f prime of 1. And that would be the derivative at this point right here. That instant point right there. Let's just go ahead and plug in our formula and see if this works out. So we're going to say the limit as h approaches 0 of f of, we're plugging in 1 plus h minus f of 1 divided by h. All right, so let's plug our variables in. 1 plus h, we're plugging into our function. So we're doing 2 times 1 plus h. So this is equal to the limit as h goes to 0 of 2 times 1 plus h, because I'm plugging 1 plus h into my function. Minus, now I'm plugging 1 into my function. 2 times 1 divided by h. All right, so that's equal, I'm getting into my graph here, but that's equal to the limit as h goes to 0 of 2, we're going to distribute this out, plus 2h minus 2 divided by h. Well, this works out nicely because our 2's cancel, and we're left with 2h divided by h, which is just equal to 2. And whether with h going to 0, it doesn't matter because we've canceled out our h's and we're left with 2. That's what we would expect our slope to be. So that worked out really nice. All right, let's do one other example. Let's pretend that our function now is, let's say f of x equals x squared. All right, let's draw that again. That's x, that's f of x. So if x is 1, then in that case, 1 squared is 1. So we got a point there. If x is 2, 2 squared is 4. That's going to be a point up there somewhere. So we're going to say 2, 4. It's going to look, well, yeah, but it'll look something like, I drew that really bad. Let's kind of relabel this. It'll look like that. So that might be our 1 and our 1, and then that might be our 2 and our 4 up there. So there's our f of x equals x squared. Let's say we were trying to find the derivative at point 2. So we're trying to find the slope at that point right there. Again, let's go ahead and plug in our definition of a derivative and let's see what we get. So it's equal to the limit as h goes to 0 of f of 2 plus h minus f of 2 divided by h. That's equal to the limit as h goes to 0 of, what happens when we plug in 2 plus h? We get 2 plus h squared minus, we plug in 2, we get 2 squared, which is 4, divided by h. I'm going to bring this on down here. We're going to expand this. We could use the binomial theorem to expand this, right? But it's only squared, so I'm just going to go ahead and write it out because it's an easy one. If that were to the 10 or something like that, I would definitely use the binomial theorem, which you can see why the binomial theorem is going to come in handy with polynomials, which I'm going to show you in the next video. But let's go ahead and expand that out. So we're going to get 4 plus, what are we going to get? 2h4. We're going to get 4 plus 4h plus h squared minus our 4 divided by h. Don't forget the limit as h goes to 0. A couple things are going to work out nice here because we're going to have our 4's cancel there, and then we're left with, let's factor out an h. So we're going to be left with the limit as h goes to 0. If we pull out an h, we'll be left with 4 plus h, right? Because 4h plus h squared divided by h, and the reason I did that, you can see, is so we can cancel that h out. Then we're left with the limit as h approaches 0 of 4 plus h. Well, now here, when h goes to 0, we're getting it as close to 0 as possible. That is equal to 0 for h, right? We can just plug 0 in there, and then we're left with 4. So our derivative of x squared at point 2 is equal to 4. That's at that point in time. And that is an overview of what derivatives are and why we might use them. Now, in the next videos, I'm going to prove some things with derivatives, and we're going to dive into a few other types of things. And eventually, I'm going to try doing a couple videos because it's a little challenging to see everything on the screen here. I'm going to try doing some videos on a virtual whiteboard and see how that works out as well. But thanks for joining on the video of derivatives.